Hayley, we come to you first, and then we'll come back to him.
If you want, I can dig out my bigger slide set. I've got loads of slides.
You ready to go then, everyone? Yeah, all good. All right, he's there. Lovely. Looks like he's there. Hello. Hi, can everybody hear me? Great. Hi, my name's Mandy, and I'm the clinical lead at medicines optimization at UCL Partners. And I'm really pleased to be hosting this evening and this webinar to talk to you about my two favourite things, which are obviously pharmacy, being a pharmacist, and genomics. We've got a number of speakers this evening, so I'm really pleased to say that firstly we'll hear from Professor Mike Roberts about the Genomics Medicine Service Alliance across North Thames and the role of pharmacy, followed by Hayley Wickens from Health Education England to talk about the opportunities for pharmacists in genomics. And then from our very own Helen Williams, who'll be talking about genomics in cardiovascular disease prevention. And we've also have Aisha, who works with us at UCL Partners, who'll be talking about her genomics journey to finish off the evening. So without further ado, I'm going to hand it over to Mike. Welcome, Mike.
Thanks very much. Great, and good to be here. So, yeah, we can get on to the first slide. Great, thank you. So I'm Mike Roberts, and I'm the Managing Director of UCL Partners and have been involved in the application process for the Genomic Medicine Service Alliance for North Thames. So I want to start by giving you an overview of what's going on in our locality at the moment. As you may or may not know, NHS England Improvement put out a call for bids for GMSA applications in January of this year, with a deadline of submission for March. And of course, at that time, enter COVID, so everything was pulled back. And then the process has been reignited with some very tight deadlines for getting in both the applications, the revised applications, and the business cases behind them. More of that in a moment. The North Thames GMSA is different from a lot of others in the sense that it goes across more than one NHS region. The others are all based around a particular region of the NHS. So our application includes North West London, North Central London, North East London, Essex and Hertfordshire, with a population of about 9.2 million people, and has 10 particularly North London trusts as the partners, because they are the key genomic medicine partners, but it will include membership ultimately of all the trusts, all the provider organizations in that patch, and eventually will encompass the CCGs as well in that alliance. The whole concept is around turning genomic medicine into frontline medicine. That's what it's all about, and that's what the GMSA is going to be tasked with doing. And in order to do that, we've got to get trust from the public in genomics, so it seems to be something that they are very much engaged in and understand. We have to get the workforce engaged in that as well. And a lot of this will be supporting the NHS long-term plan. Next slide, please. Whoops, thank you. That's great. So just a bit of additional context and how's pharmacy and pharmacists going to be involved in all of this. So this document was published in 2020 as a preparation for this, in essence saying, be aware it's happening, get engaged in this work, and start thinking now about identifying people who know about genomics within the pharmacy community, and start to upskill other pharmacists using some of the resources which are available like this on HEE website, which I'm sure we'll hear about in a moment. Next slide, please. The timelines I mentioned are quite short. The bids were all submitted last week, so the North Thames bid went in. We'll know by the 11th of December whether we're successful or not. We've had already a number of discussions with NHSEI, so we're very confident we will be successful in the bid, and the whole thing kicks off in the middle of January. So that gives us roughly 4 weeks from the time that we're told you're ready to go, from when we're actually supposed to be delivering something. And that 4 weeks includes Christmas and New Year. So we've already set out can we just go back again, please? Sorry, we've already set out a timetable of clinical director advert, which will be recruited. That person will be recruited by the end of December, and the number of other roles, which we'll see in a moment. Those adverts will go out next week, including one for a senior pharmacy representative in this. We then have to write transformation business case programs to submit to NHSEI by mid-February, which will basically outline what we're going to do with the GMSA and what funding we need to make that happen. Next slide, please. So this is the governance process. It's really complicated. I don't want to go through it all with you. The stuff in grey is what already exists. So this is building on the current genomic laboratory hubs. So those people already exist. Those systems already exist. It's the blue and upwards, which is going to be new. So the blue area are the new clinical leads. So you can see a chief pharmacist in there who will be part of this team, led by a medical clinical director and a chief nurse. They will report into a board, which will include representatives from those 10 trusts, who in turn will report to NHSEI. Now, UCL Partners is going to host this organisation, and staff who are part of the GMSA who don't have a substantive NHS contract will be employed by UCL Partners, and there will be some accountability to the UCL Partners board for the use of funds through the GMSA board. There will be a clinical senate, at which there will be representation from all the trusts and the STPs. So that's 6 STPs for us, and all the trusts as well will have representation there from clinicians, and there will be a patient and public engagement panel as well. Next slide, please. So for pharmacists, there's sort of 2 levels of engagement. One is at the senior level, which is about developing the strategy and the business case. So we're going to be looking for people to help with that work. As soon as we've got our senior clinical lead in place, we're going to have to lead that work. And then on the ground, operationally, how do we deliver all this is going to involve pharmacy as key pharmacists, as key people in making all of this happen. There's going to be sharing across the GMSAs around the country, because nobody knows how this is going to work. So nobody's got the surefire win plan. We're going to be going along a little bit and developing ideas, testing them out, and working collaboratively on this. Next slide, please. So practical steps have been suggested. This is an NHS document. I've just taken some bits from this. So as soon as we have a chief pharmacist appointed, that person will be mapping stakeholders and networks that already exist, looking at the engagement we already have in genomics across the pharmacy community, and starting to design a workforce development strategy. And then there's a number of specific things here in that more densely packed paragraph, which are the things that will need to be incorporated into the business case for the proposals for what we're actually going to deliver in the first 1 to 2 years of the GMSA. And the next slide, please, tells you what those priorities are. So we have to deliver the 100,000 genomes project. We have to deliver familial hypercholesterolemia diagnosis, so screening, testing, counselling and management in primary care. So that's really important shift. This is not about tertiary centres like Gosh delivering this programme. This is about primary care across the whole of North Thames delivering it, and Lynch syndrome, which is a multi-system cancer syndrome. And then the deliberate mistake on this slide is that we're talking about a local priority which has been identified, which is about screening for dihydropyrimidine dehydrogenase deficiency for cancer drug use, particularly 5-FU and not methotrexate. Next slide, please. So basically, that's it in a round. It's all about to kick off. We're all going to be finding our way a little bit. No question at all that pharmacy is going to be really key to what we do, and we need people to come forward, particularly to apply for this lead pharmacist role, but everybody we need to try and get behind this work. There's a huge opportunity here to revolutionize medicine, to turn this into personalized medicine. Huge research opportunity in all of this as well. And we're proud to be part of this advance guard. Thank you very much.
Thanks, Mike. Thank you. That's really exciting to hear. So just take one question before we move on to Hayley. So if anybody wants to find out more, particularly around primary care, I'm thinking, Mike, are they best to contact you?
Yeah, I think at the moment the first point of contact, because in terms of the staffing of the GMSA, there isn't anybody at the moment. You'll be sending to an empty email box. We'll have our first people in post at the end of December. So if you want to know something more, email me and I'm happy to send the email to the right people to give you information.
Lovely. And we can pick up, we did send some email letters out over the summer, so we can pick those up as well with the medicines optimization committees and all the STPs would be a way forward once we know who those people are. Thank you, that's lovely. Just moving now on to Hayley. Hayley, over to you. Thank you.
Great. Thanks very much, Mandeep. Thanks for the invitation to come and talk to everybody this evening. It's really nice to be here. As Mandeep said, this is two of her favourite things, genomics and pharmacy. Similarly here, actually, some of the names on the call I recognise. Hello, old friends and new. I've been a microbiology pharmacist for donkey's years, probably 20 years now. May have worked with some of you previously at Imperial. And my most recent job was at Southampton, but I left there 2 years ago and I now work for HEE, so Health Education England. I look after all the pre-regs in the hospitals across the south of England. But how does that link in with genomics? Well, while I was at Southampton, did an MSc in genomic medicine, and I've become utterly convinced that genomic medicine will completely change the way we deliver medicine generally over the next 5 to 10 years. And I really do believe that pharmacy and the pharmacy teams should be front and center in this. Now, I've only got 15 minutes, which, as if any of you know me, you'll know I tend to go on for hours on end. I haven't got that today, so I'm going to do my best to just tell you a few little bits about where I think pharmacy can make an impact in genomics. So next slide, please. Okay, so I've taken out all of the background stuff about genomics versus genetics and left this one in, just because I think it's worth remembering that your genome is 3 billion bases long. That's a vast amount of information. So remember your old base pairing, which is A with T and G with C. That all lined up, if you stretched out all of your chromosomes end to end, you've got 3 billion letters there. And a single change in that can give some profound genetic conditions such as sickle cell or chondroplasia. A lot of the things that we'll be looking at and looking at the drugs to treat are bigger scale changes, so big patches of DNA moving or changing or swapping. Also, sometimes you have multiple changes across the genome which contribute to a disease outcome. And this is where we can look at drug targeting as well. But just, I think this is mind-blowing that one single letter change out of that 3 billion can give you a profound clinical effect. So next slide, please. So again, whistle-stop tour. So we're talking about genomics in diagnosis and treatment, just as a bit of background. Yep, next slide, please. So we're talking about personalized medicine here, and you'll hear that a lot, sort of interchangeable with genomic medicine. And basically what we're doing is looking at the most personal of personal information, which is your genome, and tailoring treatments for you based on that. So either we can use that sequencing to classify your disease. So I'm not just talking cancer here, but things like developmental difficulties or metabolic issues, or we can talk about different things as well around infection. I'll do that in a minute. But we can assess the susceptibility of particular diseases to particular drugs, predict your response to drugs, whether you're going to get a side effect. Often changes in your genome can mean you will get a side effect to a particular drug that another person wouldn't if they didn't have that particular variation at that particular point in their genome. We can predict your response to drugs. We can choose the best treatment. Also cancer, and Mike mentioned the 100,000 Genomes Project. That's a big project that, as the name suggests, sequenced 100,000 genomes. Half of it was cancer, half of it was rare disease. So half of those patients going into there were having their genome sequenced from cancers and compared to their baseline genome, so their germline genome. So what we do is we take the genome from, say, a white blood cell, sequence that out, take the DNA from a cancer, so you've got sarcoma or something, and compare the sequence and see where things have been switched on or switched off. Cancer is a disease of disorganized replication, and lots of switches being switched on within the cancer cell that make it grow uncontrollably. And we can see where those switches are in that variation in the genome compared to the germline genome, and then maybe target those with drugs. And finally, we can use DNA from infective organisms. Of course, being a micropharmacist, I love this stuff. We can use it to pick out what pathogen you've got. We can look at whether they're susceptible to drugs, and we'll talk about that a little bit later. Next, please. Okay, here's an example of a genomic drug class, something that we use in chronic myeloid leukemia. Apologies if we've got cancer pharmacists on the line, because I'm not a specialist, so bear with me. Can you click through, please, so that I can see what's on there? Thanks. Okay, so if you look at these chromosomes here, I haven't had time to go through the background of how these things are organized, but you've got 23 chromosomes arranged from the biggest to the smallest. Number 1 is the biggest, and sort of going down as per number. So if you look at chromosome 9 and 22, we've got the red and the blue ones here. On those chromosomes, you have two little regions that can sometimes translocate, so bits swap on the end of those chromosomes. And you can see in the picture on the right hand side, what's happened here is the bottom bit of chromosome 9 has translocated with the bottom bit of chromosome 22, and that can actually be seen down a microscope, believe it or not, if you've got a very skilled operator. But what happens in this case is two parts of genes get put together that would not normally be together. So you've got, it's actually labeled BCL, it's BCR, but doesn't really matter. BCR coming from chromosome 22 and ABL coming from chromosome 9. Now, that's called a Philadelphia chromosome when that happens. Now, ABL, that normally sits quietly, does its normal thing on chromosome 9, is an auto-inhibited tyrosine kinase. Now, what that does, tyrosine kinase is like an accelerator pedal within the cell. So it means that when that enzyme is activated, the cells go, 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 divide, divide, divide. Normally, ABL auto-inhibits itself, which means that part of the protein that comes from the transcription of this gene latches onto itself and stops the thing being expressed. So it switches itself off as its base state. However, when the gene moves onto the Philadelphia chromosome, so onto chromosome 22, it becomes switched on all the time. So BCR-ABL on this Philadelphia chromosome is an always-on tyrosine kinase, which means the cells just divide, 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 and that gives you chronic myeloid leukemia. And the vast majority of CML, you will see this. This is one of the most common causes. Now, what we can do is use tyrosine kinase inhibitors that specifically target that gene, and they reduce progression to blast phase and therefore increase survival. These were hugely game-changing within treatment of CML, and you'll know the name. It's Gleevec, so imatinib. They bind onto the BCR-ABL site and stop it expressing. So they improve survival hugely and a great success. So next slide, please. Oh, there we go. So another example, and this one's close to my heart, genomics in antimicrobial resistance testing. So this is brilliant. England were the first to do this. So this is actually a few years old now, 28th of March, 2017. As you will know, tuberculosis is a disease that is A, very slow to diagnose properly in the lab, and B, it's very slow for us to get an antimicrobial resistance sensitivity pattern. So whereas when you send a urine sample to the lab, it takes 24 hours to get a bug and then another 24 hours to get a sensitivity. If you're doing that with TB, Mycobacterium tuberculosis grows really slowly, so it takes weeks to get a positive culture and then another weeks to get the sensitivity testing. So it can take up to a month to 6 weeks to get sensitivity pattern. And that means you are, from clinical diagnosis and from smear positive, you are looking at 4 to 6 weeks of best guess antimicrobial treatment for TB. Very often that means people have to stay in hospital while you make sure they get it right. But this cuts it down to just a week. So we can choose those correct drugs due to sequencing of that TB organism. It's done at the PHE lab in Birmingham, and it results in a week. So it's making a real clinical difference. This is amazing. So next slide, please. And why do I think pharmacists should be pharmacogenomics experts? So there's that word, pharmacogenomics. So it does what it says on the tin. So it's the genomics of drugs, basically. So next slide, please. Now, oh, I've lost my N off the end. So more than 100 drugs have a known genetic component, and I would say it's probably much higher than that now, actually, in terms of their metabolism or their mode of action. So here are some obvious ones, well, not necessarily obvious, but that you may not have known, but genetic variation influences your metabolism of codeine, influences whether you're going to get side effects with certain drugs. So one instance is flu clogs. Okay, now we use a lot of flu clogs. Micropharmacists use a shed load of flu clogs. Now, this is a particular genetic type or genetic variation. That's actually a major histocompatibility complex part of the genome, HLA-B570101, that particular variation in that bit of your DNA. If you have that and you get given flu clogs, you have a much, much, much higher risk of liver injury. Now, the Americans don't use flu clogs because they consider it a high risk for hepatotoxicity. And now this is probably what is doing it. And we don't currently screen for that. Okay, so next bit, please. Carbamazepine, this is on the data sheet. If you haven't looked at this carbamazepine data sheet recently, have a look. This particular genotype, again in the MHC, if you have this and you're in the Asian or Han Chinese population, it's almost nailed on that given carbamazepine, you will end up with Stevens-Johnson or toxic epidermal necrolysis. So this is we're so confident about this that this is now mandatory. You have to screen for this if you're going to use carbamazepine in this population. Another variation increases the risk of 10 and SJS in Europeans and Japanese. Now, important point here is a lot of the research in genomics has been done in North American white males. And so there's been a conscious effort over the last few years to try and increase the number of people from different ethnic backgrounds going into the genomic studies, because you just wouldn't pick this kind of thing up. So there's a sort of lots of ethical stuff around how we recruit for trials. Honestly, I can go on about this stuff for hours, I won't, but anyway. Next, please. Okay, yeah, so you don't have to screen when you start carbamazepine in European populations, but you do in Asian populations. Okay, another one, azathioprine, TPMT inactivates azathioprine and 5-mercaptopurine. 90% of people are homozygous, so you've got 2 copies of each gene. Do you want to go back one? Just back one, thank you. Thank you. So 90% of people have 2 copies of the high metabolizing gene. 1 in 10 have 1 of each, so they're sort of in between. And next one, please. Just under 1/3% of people are homozygous low metabolizing, so 2 copies of the low metabolizing form of the gene. Now, if you are given azathioprine or 5-mercaptopurine and you are the low metabolizer, you can get a massive myelosuppression. Secondary leukemias, myelodysplasias, it's absolutely, it's quite clear there's something going on here. You can do functional testing within red blood cells to do this, but you can also run the genome sequence. And the costs of genome sequencing, I've had to take out all my slides about this, but the cost and the speed has dropped hugely over the last 10 years. So gone from the first genome took 12 years and cost $30 billion or something, or £30 billion, that's a lot of money. And now we can do it in under a day and it costs about £600 to sequence. So you can see the tech is getting quicker and is getting cheaper. So the weighing up the balance of what type of test you do for this sort of thing is changing. So next bit, please. Okay, so functional testing. Next bit. So 56 drugs at the moment, this was a couple of weeks ago, might be wrong now, have a genetic testing requirement in your SMPC. So have a look next time you're opening up medicines.org. Have a look. There are a lot of places, a lot of drugs that need this kind of testing. So next slide, please. This is what I call the Martindale for pharmacogenomics. It's PharmGKB. Don't put PharmKGB in, it won't work. Pharmacogenomics knowledge base. So there's lots of monographs on here about drugs. It's going up every day. So if you just click through, please. There you go, so you can have a look at those. Really interesting piece of work from, or a couple of pieces of work from the Netherlands, one from Groningen, where they, can you click down, please? Thank you. If you stop there. This particular piece of work, they looked in 300 outpatients. They screened them for 36 variants in 15 genes using their national pharmacogenomics guide. They used the clinical decision support. This was all driven through pharmacists. So keep clicking down, please. And in Leiden, they had something called implementing pharmacogenomics in primary care. They only looked at 8 genes, and in 200 individuals, over 95% of them had at least one actionable genotype, just in those 8 genes. So you can see there's some cytochromes there, DPYD, which has been mentioned already, TPMT, which we mentioned, VCORC1 is a warfarin one. So 95% of those 200 individuals had an actionable genotype just from those 8, and we know there are hundreds of these. 10% had more than 4. So a third of patients were either closely monitored, had a dose adjustment or drug change. This was all done by pharmacists. So if you click through, please, there's a nice comment from the papers, which says, for this to work well, multidisciplinary approach, including clinicians, geneticists, and pharmacists needs to be used. We like that. We like being name checked. Next, please. I feel like Chris Whitty. Right, just a quick bit about stratification. I mentioned that we can look at people's genomics to tell whether they are going to have an adverse reaction or whether the drug is going to work at all. So what you want what we've done previously for all the years we've been using drugs is we have that group in the middle, same clinical diagnosis, we give them the same prescription, okay? And what you want is people to go into group 3 where the drug is not toxic and it's beneficial. Unfortunately, we do sometimes get drugs toxic but beneficial. So that's number 1. So the drug's working, but it's toxic. Number 4 is the bit of a waste of time because the drug is not toxic, but it's not beneficial. So you're just wasting money giving it to the people. It's not doing anything. At least they're not getting side effects. Great. The worst group is group 2, where your drug is toxic and not beneficial. We can start to use genomics to stratify patients into the groups and avoid giving them drugs that don't work or are going to be nasty for them. So click through, please. Okay, so an obvious example of this, which I'm sure you're already aware of, is Herceptin. So we're looking for a cell marker in breast cancer to see if somebody's HER2 positive, to see if they'll benefit from Herceptin. If the marker is absent, we don't prescribe Herceptin because it's not beneficial. So we take out groups 2 and 4, okay? If it's present, we know that the drug's going to work. So it's groups 1 and 3. Okay, click through, please. And this is another one, abacavir. We already do genetic testing. This is in the data sheet, the SMPC for it. So we look for the particular genetic variant. We know the drug works. The drug always works on HIV. It just does. So what we're looking for here is the risk of toxicity. So we don't give it to people who've got the particular marker, and we can avoid putting people into the toxic groups. So next slide, please. AHSP, so the American Pharmacy Associations, have already put out a statement about the role of pharmacists in clinical pharmacogenomics. Okay, click through, please. You might as well click all of these. Okay, so they've suggested some things that pharmacists can do. So we can recommend the particular tests, the drug and dosage regimes. We can educate patients and pharmacists and other healthcare professionals about this and help them choose tests. And we can write things in notes. And depending on how specialist you are, you can write guidelines, service development, and maybe acting within those GMSAs, drive strategy and development. Next slide, please. Okay, I told you I could go on for ages. I've got 3 more slides. I'm going to get through these quickly. So next one, please. Workforce development is something that I'm really interested and passionate about. But the current offer is absolutely person-led. So we've got people on the call who are doing various bits of postgraduate education and certificates, diplomas, MScs in genomics, but it's all about the individual going, yeah, I fancy that, just as I did. But the GMSAs are going to need trained staff, and I think we need this to be system-led. I'm currently working within a group within HE and NHEI looking at workforce development in this area. Next, please. But I do believe that pharmacy should be front and center. We're scientists. we're also great at communicating with patients. I think, you know, we can do the science, but we can also do the clinical. And I think it's really important that we get involved in the sort of risk assessments and the data behind some of this stuff. Things like formulary, multidisciplinary team advice, genomic passports, as I was saying. I think we can do this stuff. Next. Thank you. You're being lovely, whoever's putting these forward. Thank you very much. But we do need a surface specification for pharmacists in genomics. The roles are emerging, as we've heard already. The level of training required will vary, but I do believe that everybody working in pharmacy needs at least a basic training in genomics, because anybody can walk onto that ward or walk into a pharmacy in the high street and say, I've got this direct-to-consumer genetic test from one of the commercial companies, Ancestry, 23andMe. They've shown me I'm carrying sickle cell trait. What does that mean? So we all need to be able to have that conversation, whether you're a pharmacist, whether you're a technician, you need to be able to have that. And yes, you'll need a few individuals with the sort of more specialist genomics knowledge, particularly in the strategic roles, but I think we all need to do this stuff. Services are changing around this. I haven't had time to talk about it, but we're remodeling cancer services. So instead of being lung cancer or hepatic cancer, you will find a similar mutation in both of them and maybe treat from a mutational basis. So it's very interesting. Next, please. And what training's available? This has already been mentioned. HEE has a genomics education program. Please go and have a look. Loads and loads and loads of free resources. They are excellent. I absolutely endorse these. There are 5-minute videos. There are right the way all up to full modules at MSc. So keep going, please. There are MOOCs, so massive open online courses. There are 2 on FutureLearn at the moment. There's an HEE one and a St. George's. It's a brand new CPPE genomics module, which I thoroughly recommend. It's really cool. So you can search all of those and you'll be able to see the slides afterwards for the links. But there's so much free stuff out there. And HEE also fund full-time MSCs if you want to do that too. So keep going, please. And just a very self-indulgent slide showing you where drawing parallels between antimicrobial stewardship pharmacists and genomics. So you can click through all of this if you want. Back in 2000s, when I started doing this, there were 6 genomic specialist pharmacists in the UK. Then we got an infection management group within the UK CPA. There was an MSc launched. And then by 2005, we had 140 posts. We got the first consultant in 2007, nearly 200 posts by 2011. So 10 years in, 11 years in. And now there's it's probably slightly higher, 600 members in the pharmacy infection network. And this is where I think we are going with genomics, because if you click through, we've got specialist pharmacists who have trained in this. I think we've got 29 pharmacists who've done the full MSc and hundreds of people who have done modules. We've got a genomics group within UK CPA, which I would encourage you all to join. If you're members of UK CPA, please do, more than welcome. And I think we've got about 35 of us in there at the moment. So I think we're on that similar path where we have micropharmacists, often plural, in every trust, and specialist technicians. And I think that's where we're going with genomics. So next, please. So what are the challenges? Building and development for everybody. So keep clicking. We have a lot to do. We have a lot to cover. We already cover an awful lot, and we know there's a review initial education and training at the moment, but what can we put in there? What do we drop? It's already busy. And the science is moving faster than the societal discussion. There's a lot of stuff out there that's readily available to the public. And I would argue that the discussion around whether we should do some of this stuff has not been had as a society. So we have a role as science communicators. But I would encourage you all to be bold, understand the potential of pharmacy in the field that's emerging, and have a think about what you do in the next 6 months. So you click through, please. I've gone over my time, but I'm still within my deadline. So I hope that's okay. Here's a bit of further reading for you. Please do feel free to drop me a line if you'd like to. And there's my Twitter handle as well. So thanks very much for having me. I'll shut up now.
Hayley, thank you. You've done really well. You've kept to time. We're right on time. So thank you. So I think that really gives us a great overview. I think a lot of people, myself included, thought this was going to be very, very specialist a couple of years ago. I think, if you look at the drugs that you've mentioned, Fluclox, warfarin, those are all, drugs that we all see in primary care routinely. So it's going to be important for us all to have an understanding. And I get very excited at the fact that we can, finally be able to predict those patients that will have adverse drug reactions and prevent them from having those medicines will just be amazing, won't it? Because that would... that's what we want to do, is reduce harm from medicine. So thank you very much. We will take some questions. If anybody does have questions, please do put them into the chat. But I will now move over to Helen for her presentation of genomics in cardiovascular prevention. Thank you, Helen.
Thank you, Mandeep. I'm going to focus mainly today on familial hypercholesterolemia. It's one of the local and national priorities. And now my iTunes has just launched, apologies. Try and get rid of it. Okay. So, in terms of ambitions at a national level, we have, within CVD prevention, we have 3 ambitions. AF, to improve detection and prevalence, detection and treatment, particularly anticoagulation. High blood pressure, again, around detection and management. And for high cholesterol, we have 3 core aims. 1 is about ensuring patients get cardiovascular risk assessment. 2 is ensuring that people who are at risk of cardiovascular disease, so needing prime prevention, are offered a statin. And 3 is that patients with familial hypercholesterolemia are diagnosed and treated optimally. And you'll notice there the figure, we're aiming for 25% of people with FH being diagnosed and treated, which seems really rather low when we look at the 85% we hope for AF and 80% for high blood pressure in terms of detection. So we do have an issue with cholesterol. It has been a bit of a Cinderella compared to AF and blood pressure for many years, and it's nice to see FH and more broadly lipids coming back into the fore. Next slide, please. So currently, we estimate that only 5% of our patients with FH are actually detected. So that is pretty poor when you think about the consequences of FH, which we'll go on to in a while. And that's why, you know, we're looking to increase that 5-fold over the next 4 years or so. We're already a year into the ambitions. So it is really time for us to knuckle down and start trying to identify this cohort of patients. Next slide, please. And genetics can help with that. So FH is a dominantly inherited genetic disorder. It affects about 1 in 250 individuals. We have worked to an assumption of 1 in 500 until relatively recently. So it is much more common, and that actually has been one of the biggest challenges in managing FH, particularly in terms of its genetic diagnosis. Most genetic disorders that we've looked at in the past have been, you know, 1 in 100,000. So we're not, you know, it might cost a bit to find them because the genetic costs are expensive, but they were low volume. In FH, we're talking about 1 in 250 individuals, so quite a substantial portion of the population. It is characterised by very elevated LDLs, and we'll look at some of those levels, and therefore early onset of cardiovascular disease, so heart attacks and strokes, etc. So patients with FH have somewhere between a 2.5 to 10-fold increased risk of having cardiovascular disease compared to those who do not have FH. And you can see here studies showing risk of developing coronary heart disease up to 13 times higher if people have untreated FH compared to those that don't have FH. We know that if we can identify FH early and treat it well, then we can reduce the risk of cardiovascular events very substantially. There's very few interventions that can show an 80% reduction in risk for patients. But the challenge we have, as I've already highlighted, is most people with FH have not been diagnosed and are therefore not treated. Next slide, please. So just a couple of statistics. If we leave men with FH untreated, about half of them will have a heart attack by the age of 50. And if we leave women untreated, about 30% will have a heart attack by the age of 60. So a huge motivation really for us to do more for this cohort of patients. Next slide, please. And we know that we have treatments that work. So the red line here, the red dashed line, shows the event-free survival for patients with an FH diagnosis. over 12.5 years of follow-up. So you can see these patients either die or have non-fatal stroke or other cardiovascular events. If they're treated with a statin, that is substantially reduced, such that, you know, over 12 years, there's about a 20% rate of event rate versus around 60+% in those that receive no treatment. So huge benefits from statins as a starting point, and obviously these FH patients need aggressive lipid lowering, and we now have newer therapies that we would add on top of statins to further improve their outcome. Next slide, please. So we've heard a little bit already about how disorders are passed down through our DNA, and you can see here a mother and a father. At the top line, the mother has a FH mutation. We'll talk a bit about what those might look like a bit further on. Mostly they are affecting the ability of the body to clear cholesterol, so affecting the LDL receptor. The father has no genetic disorder related to FH, and the offspring, well, 1 in every 4 is likely to have heterozygous FH, so a single gene mutation. Sorry, 2 in every 4. If you look at the bottom line, however, both the mother and the father have a genetic mutation, an FH mutation, and you can see here there is a risk that they will end up with a child that has both faulty genes effectively, so a double mutation, homozygous FH. And when you do have that, the cholesterol levels are even more significantly raised. Next slide, please. So if 2 people with heterozygous FH have a family of 4 children, on average, 2 will inherit the normal form of FH, so a single gene mutation, which is the most common version. 1 child will inherit the most severe form of FH, homozygous FH. And these patients, these children actually develop cardiovascular disease because the levels of cholesterol are so high during their, during their childhood, even before the age of 10, and certainly during their teens. And 1 child, in the laws of probability, will not inherit FH at all because they'll get a healthy gene from each of their parents. So this is average, obviously. We don't often see a family of 4 that results quite like that, but that would be the probabilities of how 4 children would emerge from that coupling. So next slide, please. So this shows you it in a different way. If you imagine you are here with your FH, in order to have FH, at least one of your parents would have had to have it. And if you have a child with someone who doesn't have FH, if you have more than 1 child, the chances are you will end up with a child with the FH defect. Your parent, if they have multiple children, may produce children without any FH defect, or may produce other children with the defect, and it will pass down the family line. If you end up in the circumstance where you don't have FH and your partner doesn't have FH, then you cannot produce a child with FH. Next slide, please. So the big challenge we face when we look at FH is how do we find those 1 in 250 people with FH and ensure that they are diagnosed early and treated as early as possible. And that's where we are at the moment. Genetics can help us do this, because if we find 1 person in a family with FH, we can test their relatives and identify those within the family that also have FH, because it's passed from generation to generation. Next slide, please. So one of the reasons we often don't pick up FH is because there's an overlap between a normal cholesterol range, which is shown in the dark green. Unfortunately, this is American units, but just to give you an idea, 200 mg per deciliter is around a cholesterol of 5 millimoles per litre. So you can see that the dark green distribution does overlap once we get into the sort of 4s, 5s, 6s of cholesterol with the heterozygous FH population, where the cholesterols you can see are substantially raised. often, you know, in the order of 8, 9, 10 millimoles per litre. And then beyond that, the homozygous FH population is sitting there as well. And they can have levels of 15, 20, 30 millimoles of cholesterol. A small population, but important nonetheless. Next slide, please. So just to say that in terms of homozygous FH, there's probably only 100 or so patients in the whole country, and we've probably found about 70 of them at the moment. So they're a very specialist cohort that needs very aggressive intervention because their cholesterol levels are so high. The vast majority of FH is heterozygous. And in the past, the way we've diagnosed this is by looking at the cholesterol level and other signs and symptoms. So a definite FH using the Simon-Broom criteria would be cholesterol within the ranges that you can see in the table, and tendon xanthomata in the patient, and I'll show you some pictures in a minute, or evidence of them in first or second degree relatives. So it requires quite a significant assessment. The other option we have is to actually look for the gene mutation and identify those patients by doing this gene sequencing. And that is where we are moving towards, because it is, you know, it's not very specific to use cholesterol levels and some of these signs and symptoms. So the Simon-Broom criteria defines people as definite FH and probable FH. So again, leaving some uncertainty about the diagnosis. Next slide, please. You need to look for these sorts of things which would also support the diagnosis. So xanthomata in the tendons. So this is in the hand, you can see here, and also in the heel. It probably doesn't come across quite so well there. This patient, it's not very specific, this sign, this has corneal arcus. You can see in the eye, in the top right picture of the eye, the arcus. I'm putting out my screen, but realizing you're not actually looking at my screen, you're looking at someone else's. So that's not helpful. And then the fatty deposits around the eye in the bottom picture, xanthelasmata, which I know I never pronounced correctly. So we can do these assessments. Obviously, it takes a while for these deposits to, these signs to emerge for patients. And there are, with the DNA testing, there's obviously a greater opportunity for us to identify these patients much earlier. Next slide. So FH is a genetic disorder, dominantly inherited, as I've said, and most of the mutations affect the LDL receptor gene, and the LDL receptor is essentially responsible for clearing cholesterol from the body. So if you have no LDL receptors, your cholesterol levels go sky high, and if you have lots of LDL receptors, your cholesterol level will fall. And most cases of homozygous FH are due to total failure of the LDL receptor. But there are lots of different mutations, and obviously in some of the mutations, the receptor totally fails, the receptor is not present, it's not being made, but in most, the receptor is there but defective. And the activity of the receptor will affect what the cholesterol levels look like. So those that have no receptor activity will have much higher cholesterol levels or LDL levels than those that have a defective receptor. Next slide, please. So there are other gene mutations. So LDL receptor is the primary, familial hypercholesterolemia, ApoB, again affecting LDL metabolism, PCSK9s. So many of you may know that we now have PCSK9 inhibitors, so lower cholesterol, and there's also a specific gene mutation. There's some populations and whole families that have no PCSK9 function, and they have very low cholesterol levels and virtually no cardiac disease, and other populations in the world that have excessive or gain of function, so much more active PCSK9, and have very high cholesterol levels and therefore high cardiovascular risk. And then finally, this LDL RAP1 receptor gene disorder. So next slide, please. So once we have found a patient with FH, once we have identified our index case, we know what the gene defect is. We can then test their family. And this is first degree and secondary degree relatives. It's much more cost effective because it costs a lot, or it costs some additional money to find that first index case and what the gene mutation is. But once you know it's there, all you have to do is look for that specific gene mutation. So it costs about £250 for the first test to find your index case, and then screening for those family members is about £40 to £50 per test. The biggest challenge, of course, is these days we don't live in our own, you know, in an enclosed geography like we might have done generations ago. People are scattered across the country, so we do need quite a strong, robust system for tracking these family members and making sure that the tests are undertaken. But the beauty of cascade screening, we've seen in other countries like the Netherlands, where they've done it very effectively, with a dramatic increase in the number of patients with FH who are treated with statin, which obviously impacts on longer term outcome. Next slide, please.
Helen, we've just got a minute or so, please.
Yeah, I'm just going to show you one family and then I'm just about done. So in this case, our index case marked here is a patient who has 2 gene mutations, one from the mother and one from the father, and their cholesterol was 18, so a homozygous mimic effectively. This patient's mother actually married 3 times, and their first partner did not have FH, and they produced a child with a normal cholesterol. She married the individual on index case, his father, who had a different gene mutation and had a cholesterol of 7.8. He went on to remarry and had one child with a normal cholesterol and one with the FH gene mutation. So you can see how it tracks through families, and even above that, the grandparents, obviously one of the grandparents had to have the gene mutation that was passed from mother to daughter. And the average cholesterol levels with the normal patient, the heterozygous and the homozygous mimic, this patient here, you can see the average cholesterols are substantially raised. So final slide, I think, is just to say where we are now. We've heard some of this already. 7 national genomics hubs identified, FH a national priority for detection, and we're just awaiting final confirmation that the funding has been released for the genetic testing for FH. We need to start thinking of pathway redesign, identification of patients, search tools, triage, referral if necessary, depending on where the genetic counselling and the cascade testing is going to happen, and then the ongoing management. And just a comment that there's also some pilots that are looking at screening children in the very early months of life to then identify potential parents with FH. So that's a new pilot program looking at child parent screening so that we can identify FH patients through the child parent relationship from virtually from birth. And I'm going to finish there and hand back to Mandeep.
Lovely, thank you so much, Helen. We have some minutes now for questions. So we've still got Hayley, Mike and Helen. So if you have any questions, either type them into the chat box or you can unmute yourself. I probably just want to start off with FH, Mike. I know that's in one of the top 4 priorities. What kind of timelines are we looking at for that testing to be available? I know there's some work that's being done up in the northeast looking at testing.
So testing's already available through the genomic lab hubs. It's a question of identifying the right people and finding the funding to make sure that if we go into a mass testing program that we can afford it. So I think the business cases that we'll be writing for that February submission date to NHS England will be around that. How are we going to be trying to identify people in the most cost-effective way, and how are we going to be treating them and managing them and putting that business case in? So we're ready to go, and by 1st of April we'll be rolling out a program. So we haven't got much time.
No, and that programme will be for input from primary care for those patients.
Absolutely. I want to really stress this. This is about moving concept from tertiary centres into frontline medicine in primary care. So this is about upskilling those people working in primary care, whether they are pharmacists, practice nurses, GPs, optometrists for that matter, because we've heard from Helen about the need to diagnose xanthelasma, for example. All of those areas will need to be part of this training programme that we'll have to facilitate through the GMSA.
We have some, I know we have some senior colleagues from primary care and CCG, so it would be really great to be able to engage with them as soon as we can. So if we have any queries from them, that would be great. There's a question here from Laura. Is there a difference in adherence to statins in people with FH versus non-FH high cholesterol?
There is some difference in adherence because just by nature of the disease, many of these individuals will have seen parents and grandparents who've had very early cardiovascular events. So there's actually a driver really for them to adhere. Plus, many of them at the moment getting quite significant support through FH specialist centres and the genetic counselling, the need to test children, etc. I think it hits home much harder for people with FH than it does for our routine CVD primary and second prevention, because they have seen it through their family. Often people don't know that what grandma died of, but she died at the age of 45 of a sudden event. And if you know you've got FH in your family, it's likely that was the cause.
And can I just add in, sorry, that also the Acceleration Access Collaborative is launching the PCSK9 inhibitors as treatment for FH as well this year. And they part of our commercial and innovation team's role will be to support the rollout of those and the use of those in routine practice. And the other star that's coming into the heavens in an alignment is that the AHSNs are to be commissioned to roll out a program of detection and management of familial hypercholesterolemia. So Laura, who raised that question, is going to be one of the people leading that program for us.
Lovely, thank you. Another question we have from Amelin. So is there a list of medicines with summary product characteristics, you're now testing me, genetic testing requirements, please? So is there a list somewhere, Hayley?
There might be one somewhere. I don't have it. Somebody told me that on good authority how many numbers there are. I think it's probably higher than that now. I can try and find that for you because I think it is in existence, but I don't have it on me.
Yeah, and also I suppose for us to know where that's going to be maintained as well.
I think the best thing to do actually is to go on to pharmacogenomics knowledge base. So if you go on to PharmGKB, because that is updated constantly, literally every day, they put another monograph on there. And so even if I gave you a list today, it would be out of date by tomorrow. So it and even though they may not, there'll be a difference between the number of drugs that have it on their data sheet and what's on the GKB. So I would actually go there and have a look at it. So it's also a massive resource in terms of when you click through, it shows you all of the pathways and fabulous graphics. And you know, there are often many genes involved, and they won't necessarily be the single one that is on the spread on the SMPC. So actually, it's probably better to go and have a look through there.
Okay, I'll put that into the chat in a second again. I'll put that for everyone. Thank you. I know Helen has got to go, and I know Hayley, you've got to go as well. But I just want to say thank you very much. And another question from Aisha. So, is FH seen in any particular ethnic background more often than other ethnicities?
Yes, it is the answer. But it's not quite so obvious as you might think. So people of Afrikaans descent, so Dutch immigrants into South Africa, have very high levels. French Canadians have very high levels. but also people of African descent also have higher levels. So it's a bit of a patchwork. And I think one of perhaps the important things for us in our geography is that we have a very ethnically diverse population. And so we might be learning quite a lot about FH from the work that we do in terms of our case finding and or screening program, depending on what we do, that might well add a lot to the understanding and the knowledge about those differences in ethnic groups. Yeah.
Lovely, thank you so much, Hayley. I know you've got to scoot, so thank you so much. That was brilliant, and Mike as well. Thank you. You're more than welcome to stay. We're going to move on to a poll now, but thank you so much. That's such a great introduction. I get excited every time I hear about it. Thank you. Okay, Aisha, would you like to introduce the poll?
Yeah, so hi, we're going to do a quick poll before we go on to my talk. So the first question is, were you familiar with genomics before this session? If you just click yes or no. And then the second one is, how relevant do you think genomics will be for pharmacy? Relevant, not relevant, or no view? And third question, were you interested in studying genomics before this session? And lastly, are you interested in studying genomics now that you've heard from Hayley and Helen and Mike? So I don't know how many people have voted. I guess we've got 11 of 19 that have voted.
We'll just give it another few seconds. And then should we bring up your slides while people are still doing that? Okay, thanks everyone. Aisha, over to you.
Great, thank you very much. Right, so hello everyone, my name is Aisha. I'm working as a pharmacist advisor at UCL Partners, and I'm currently studying genomics at Imperial College. So I'm just going to give you a bit of information about my journey so far. So my career background, I started off in hospital pharmacy, did my pre-reg then in 2007, been in hospital for a few years, did my postgrad diploma there and my independent prescribing course as well. Then moved out of hospital pharmacy, went to GP practice part-time, just for a little while, and then moved over to CCG work. And while I was there, I did my Prince 2 project management course. And then I went to Academic Health Science Network in 2018, which is where I did my Darzi Fellowship in South London. And now I'm doing my postgraduate certificate in genomics, so continuously learning. Next slide, please. Thank you. So with the genomics courses, you've got different options, as Hayley did mention. So you can do a master's course, which is 8 modules, and you have to do a research project with that. There's also the option of doing a postgraduate diploma, which you don't need to do a research project for, but you still would need to do those 8 modules. And then there's a postgraduate certificate, which is what I've decided to do to get started in genomics. So I've done the introduction to human genetics and genomics already. And I've got the genomics of common and rare inherited diseases, which I'm starting next week, actually. I'm then going to do the molecular pathology of cancer and application in cancer diagnosis, screening and treatment at the beginning of next year. And the one that I'm really looking forward to, obviously, is the pharmacogenomics and stratified medicine. Now, just before I move on, I do want to say, because we haven't actually defined genetics and genomics, and I don't need to go through this whole talk and actually come out of it and think I still don't know what genomics is. So I just wanted to explain that genetics is the study of genes, and genomics, obviously, the study of your genome. And if you wanted to know the difference between what is genetics and genomics, if you think about a library, and one book being your gene, and then the library being your genome, it kind of helps you to understand the difference between the two, just so that you have a bit of an idea when you're going through and reading anything, you can really understand the difference between the two. And I know it might sound simple, and some people might be like, yeah, obviously, but I think for others, it is helpful to just make that differentiation and give that definition. Next slide, please. So my experience so far, I am working full-time, doing this part-time study again. So I did do my postgrad diploma when I first became a pharmacist. So if anybody has done hospital pharmacy, done a postgrad diploma whilst you're working, you already have experience of that. So it's nothing that will be new to you. You've done it before. And of course, it's not easy, but it's something that once you've done it, you've got that other qualification under your belt and it is worth it. So I would say if you are thinking about it and you are working full time, don't let that put you off. There's a lot of people that are working full time and doing this genomics course as part-time study, and it is possible, it's doable. One of the things that I had to obviously do was learn about the new databases. So they've got databases with genes, particularly ones that are disease causing. And when you first go onto these, so things like ClinVar and OMIM, it can be a bit of a minefield. So you go on it and it's quite overwhelming. But with anything, you continuously use it and then it does become second nature, like you're using your BNF again. So it is difficult when you start off, but you do get used to it. Definitely would advise if you are going to do the course, make sure you do find a genomics buddy. So when I did my first module, I had a couple of people that I was studying with, and that really, really does make it a lot easier. And now that I'm doing this course in Imperial, it's all virtual, so it is a bit more difficult to meet your fellow students, but definitely if you can do that, I would definitely advise that, so you can have like a little study group and talk through things. And then lastly, like with everything, it's easier if you find it interesting. So at the beginning, I did actually find it a bit difficult. I was like, why am I doing this again, studying and working and all of that? But the more I've been reading about it and the more I've been doing on this course, I actually find it really, really interesting. And just to show you how interesting it is, I wanted to do a bit of a quiz. So I think if you do the next slide, please. Yeah, can you bring up the poll, please, Shannon? If you've got one on there. Perfect. So if you could all please answer these questions for me. So the first question is, how similar do you think that human genomes are? So my genome with yours, with everybody else in the world, how similar would you say our genomes are? So 96.9 to 97.1, 98.7 to 98.8, or 99.8 to 99.9. Second question. So if you read 5 letters every second, how long would it take to read a human genome? And if you remember at the beginning, Haley said that our genome has 3 billion base pairs. So that's 3 billion letters. How long do you think it would take to read? And then lastly, what percentage of the genome do you think contains genes? So we've had 6 people vote. I'm going to leave it for a bit longer because I want everyone to try. Guess if you need to, that's fine. Just put anything down that you think is, yeah, sensible. It's not obvious, obviously, they're difficult questions. But when I found out the answers to this, it actually made me go, wow, that's amazing. And it's kind of really intrigued me more about genomics. So I hope it will intrigue you as well. Right. So I've had 12 people vote. Okay, so the answer to question 1 is actually 99.8 to 99.9. Perfect. So that's the majority of people that have put that. So I think that that is amazing to think that my genome is 99.8 to 99.9 similar to everybody else in the world. So if there was ever an argument for we have more that unites us than that which divides us, I'd say genomics is really proving it for us there, because we're only 0.1 to 0.2% different. And I think that that's amazing. So that was really, really interesting to learn about that. Second one is, if you read 5 letters every second, how long would it take you to read a human genome? It's actually 19 years. So if you work it out, if you had to read it yourself physically, it would take you 19 years to read 3 billion letters. amazing. But obviously the machinery is doing it in like a day. So it's great. And then lastly, this is really interesting because we've got an even split on all these answers. What percentage of genome contains genes? It's actually 2%. So all of this that we're talking about is only 2%. But we do know that if there's changes in the other 98%, that can actually lead to health issues as well. And there is a lot more research going on around the other 98%, but the genes is only 2% of our whole genetic data. So I think that again is amazing. I would never have thought our genes is only 2% of our whole genetic information. So yeah, I hope you guys have enjoyed that, and I hope that you are a bit more interested in genomics now and you might consider doing a course in it. Thank you very much.
Aisha, thank you so much. It is absolutely a pleasure to see you enthusiastic, because I think Aisha and I came to this in different ways. I have wanted to do this literally all my life since, you know, I learned about DNA when I was 17. And Aisha was like, not sure, Mandy, not sure. And now it's great to see you so enthusiastic about this course. It's brilliant. Thank you. We've got 5 minutes for questions, and I'm just going to ask Shannon to bring up the last poll so that we can, I think I can do it. Just if we could look at the first poll just to see the responses we've had would be great, but happy to take any other questions that people may have. Okay, so I'm going to just go through this poll. If there's any questions, just type them in or just unmute yourself. So it's great to see that everybody thinks it's 100% relevant to pharmacies. That's amazing. Great. You know, I was the same as well. You know, how familiar was I with genomics as well before I did the course in February? I thought I knew something, but to see that it's on the point of real practical application, which we know in secondary care already, but for primary care is really, it's a bit scary actually to think that, you know, we're getting there. We need to get our workforce ready to be able to support this. And everybody now wants to study genomics. Excellent, that's great. So it should be. So what I would say is, if anybody is interested, would point you to the Health Education England modules. They're bites, some of them are only 5-10 minutes as two, but there are some half-hour ones that are excellent, and it gives you a really good introduction and gives you an overview of where the application will be, you know, right from like chemotherapy, where we would expect it to be, but also, you know, using in infections and how to monitor outbreaks, and obviously in the pharmacogenetics that we've discussed this evening as well. So we've done really well today in that we have made it in time. So just want to thank all of our speakers and Aisha as well, and my Zoom fairy in the background, Shannon, thank you so much. Can't do it without you. And happy to take any questions, and we'll see you next time if there aren't any. Thank you so much.